coming in there. I know. Yep.
I have a question. What exactly makes like a bicycle stay upright?
What makes a bicycle stay upright?
Yeah.
Oh, oh, more complicated. Um, the wheels of a bicycle act as a gyroscope.
Okay.
If you take it's a lot like a top. If you take a top and you spin it,
Yeah.
that provides a force that stabilizes it.
Okay.
So even though it's on one point, it will stay. The Earth itself is gyroscopic because it's spinning.
Okay.
Yeah. So a bike, if you're just on a bicycle and it's not moving, it's way harder to keep your balance.
Yeah.
Now, but you still can. There are people who are very good at that. And you can still keep it upright because you just make sure your center of balance, that force, is straight up and down. The bicycle is supporting you.
Okay.
You go that way and the bicycle starts to fall over, then you just make your body go that way and it starts to fall that way and you can keep it upright.
Is that the same reason why like that carnival game where you have to like a rope, you have to like stay on like the rope?
Yeah, yeah. So having a good sense of balance. But the wheels add extra stability. Okay, now that I've just started the live stream, I'm going to pause it. turn this back on. So weight is a force. And pull this away.
Are we going to do a lap?
You were going to be, I'm hoping to get you out there. I have. I've been asked that we should go out there and use some of the carts. I haven't done that before. And apparently there's also a bottle rocket thing that we can do. So we might also be doing that. So I have to check with Mrs. Warner, because she's taught Physics 10 before and knows what labs to do. So bottle rocket is apparently coming up. But first we have to be able to calculate things. Weights in unit, how you would calculate weight. Weight is equal to mass times G and G on planet Earth is 9.80 meters per second squared. Gravity on, that's a G, Earth. So W is equal to mg. So what would the calculation be for that? For that, I said, we're using our 10 kilograms.
M over 5 for S2. I think so.
Yep. Vespa?
Is it
Hold it 1 second. Okay.
Is it G equals 9.80 M over
Second squared.
second?
Yeah. It's an acceleration. So if you're in a car and you're going at, say, 50 kilometers an hour, that is a speed. But if you were going 50 kilometers an hour per hour, so 50 kilometers per hour squared, what that would mean is for the first hour, you would be going 50 kilometers, and the next hour you'd be going 100, and the next hour you'd be doing 150, and the next hour you'd be doing 200. You are accelerating, so you're getting faster and faster and faster and faster. So on planet Earth, if you drop something, it will be going 9.80 meters per second first second. The second second, double that. Triple, keep going and going and going and going. The only reason something reaches what's called terminal velocity is because of air resistance. Okay, what's the mass? No, that I'm using right here. I put it right there. 10 kilograms. And I'm going to multiply that by gravity. What's the acceleration due to gravity? 9.80 meters per second squared, which is equal to, what's 10 times 9.8? 98. So we get 98. And what are our final units? Kilograms, meters per second squared, or 98 newtons.
So anytime something's meter per second squared, it's a newton.
Yep. So a kilogram meter per second squared is a newton. And energy, remember, was a kilogram meter squared per second squared, which was a joule. That means if you take a force and you apply it over a meter, a distance, you now get energy. So energy is also a force over a distance.
What's the E?
This E, energy. that make sense? Okay. I'm including all of these units just so that you can see where they come from. If you end up going, I'm just going to worry about joules and newtons for now, that's okay. If you're planning to go on in science, chemistry, physics, biology, knowing the root units is really extremely helpful. And so I want to make sure that you have an exposure to that now. Everybody okay if I move on to the next page? Everybody not okay? Okay. Masses in motion. One of Newton's laws, objects in motion will stay in motion and until acted on by another force. This is called inertia. Have you heard the phrase, shoot for the moon because even if you miss, you'll reach for the stars? Because of Isaac's laws, that is literally true. If you miss the moon, you are now in space. There is no air resistance. You will keep moving forever because there is nothing to block your motion. And you will die cold and alone in the depths of interstellar space until you hit another planetary body, which, given how rare they are, will probably be never. Unless you're really lucky and you get pulled in by the sun and incinerated in its core. If you find a black hole, that might be an amazing way to die. Spaghettification has always sounded really cool. Yeah. Santi had his hand up.
No, basically, so like, what did you say when someone gets like thrown into space, they just can't stop, or what did you
Yeah, because if you were to throw a ball on Earth, eventually, even in the air resistance will slow it down, and eventually it'll drop. Even if you throw it hard enough that it shouldn't, it will, or it'll hit the ground, and then the ground itself will provide friction and throw it to a stop. But if you lower that friction, think of like a skating rink. The ball will go a lot farther because we've reduced that friction. In space, the friction is reduced to zero. So if there's no force to stop it, once it's in motion, it will go forever.
This guy saw a movie, and I remember.
Yeah?
Shouldn't there be there should be some things that affect that? 'Cause like, let's say you were shot. What if you were
Oh, hold it. I just realized Santi's hand was up, and I completely ignored him. And then I'll come back.
What does it say there?
Which one? Inertia?
It says inertia.
This one?
Yeah.
I-N-E. That should be an R-T-I-A. Yash?
So, like, what if you're shot like really like at 1 kilometer per hour?
Yeah, then you will stay going 1 kilometer per hour forever until another force is applied. So if you manage to hit another solar system, then great. Maybe you'll hit an asteroid, drop down another planet. But they're so far and few in between. Like, most of space is empty space.
You want to slowly go like.
The only reason something goes like this is because of Earth's gravity. If you're beyond Earth's gravity, that's not there anymore. You just keep going straight forever.
So is that why like you can't stop either? Like nothing like even if
Yeah.
like when you like they say like if you're like an astronaut you like get too far from your ship.
Yeah.
Nothing can stop.
Nothing can stop you.
Like the movie.
You can't, there's nothing to swim against. Like, there's nothing to, when you swim, you are taking mass and you're shoving it behind yourself to propel yourself forward. So one of the things in an emergency kit would be a handgun, not to shoot the other astronauts, but if you had to, and you're going away from your ship, you could shoot it behind you and then throw the mass away, and then you get propelled forward. The reason why rockets work is not because they're on fire, but that flame throws mass out really quickly, which provides a force up. So it's the throwing of the mass out. Theoretically, if you're in a spaceship, and you didn't burn any coal, but you just took it and then hucked it out the back, that would provide a force.
What about that bullet? That would be fun.
That would be going forever in the opposite way. Yeah.
What if what if there was like an astronaut that already like was like let's say like the astronaut's here, the spaceship's here, and like you shot it this way, and there's like an astronaut here.
Yeah.
Would it hurt him? Like would it still like kill him?
Oh, yeah, depending on the relative speed. Getting hit by like even micrometeorites in space, they're moving really fast. They rip things up. Yes, question. Soren. But your hand was up for like a long time. No, I feel bad. Matter can neither be created nor destroyed. So, for example, if you were on a, you're in a competitive team, you're training, you're exercising a lot, and your mass decreases. Where did that mass go? Like, how does your mass physically get left? Your mass decreased. You're constantly taking in water. So that actually is mostly a homeostasis. So you didn't really lose a lot of water because you constantly drink water too. So if you permanently decreased your mass, where did that go?
Energy.
Yeah, in a way, it is energy.
Yeah.
But where did the actual mass go? Yeah?
Well, it was burned in like the mitochondria.
It was burned in the mitochondria. What does the mitochondria give off? Lipids. Gluten. What, you guys are crazy. C6H12O6, classic sugar, plus oxygen, gives off water and CO2. So when you said water, mostly right, you're constantly drinking in the water. The amount of water isn't that much. Your mass, you breathed it out. You went, every time you breathed out some CO2, you were breathing out what you were burning. If you burned more than you take in, then you're losing mass. Now, if you're building muscle and you're gaining weight, that comes from your food. You took the carbons and stuff out of the food and you broke them apart and then reattached them in your muscles. But if you burn them, they break up. And the only way to get rid of them is to burn them. It's because then you breathe out the CO2. I have had some students go like, well, you poop it out. And like, no, that's just the food you couldn't eat. You don't do any of that. There's a little bit of waste from that. Any extra red blood cells get out there. That's why it has its lovely color. But other than that, the greater the mass, the more force is required to change its motion. This is one of the reasons why we want to start looking at our sky with telescopes to figure out when the next asteroid's going to hit Earth.
Why do you want to know that?
Well, because if we find out early enough, we can stop it. If an asteroid is like on the horizon, we can see it coming, it's a bright star in the sky, it's probably too late. It's a big mass, and you're going to have to shove it sideways.
Don't we really know when the next asteroid is coming?
No. One went between us and the moon a few years back. It's a really close call. They were like, oh my God, this is going to like go through here. And they're like, okay, it's just barely going to miss us. But there's been movies made where they like shoot it with a nuclear bomb. And what you would do, and then they show it blowing up. And what's hilarious, if you're a physicist, is like, if you took a bomb and you blew up the asteroid, did you change its mass? No, it's still heading right for us. You took a really big bullet and made thousands of smaller bullets that are all going to hit maybe over a slightly wider area, so will destroy more of the Earth. Still a really bad idea. What you need to do is attach a rocket to the other side of the asteroid and just change its trajectory slightly. Now, if this is the Earth and you change its trajectory slightly, it's still going to hit the Earth. But if you can figure out when it's way back here, you don't need a very big rocket. You could, NASA just put a very small rocket on an asteroid a couple missions back. It wasn't very large, relatively recent. I think it was 2022. And they're able to successfully change the trajectory of an asteroid. The reason they did that is if we ever see a big asteroid, we want to be prepared to be able to move it. Otherwise, the dinosaur killer asteroid would also kill us. If we had no crops for 200 years, I mean, maybe some humans would survive, but it definitely wouldn't be a fun time. Okay. To make an object move, we need to apply a force. Oh, sorry.
Are you sure the dinosaurs were killed by a meteor?
I know meteors have caused extinctions. I don't know which extinctions were caused by specific things. Why? What were you thinking of?
How did the dinosaurs die?
Which dinosaurs?
So there were no dinosaurs?
He's saying that they evolved. Is that what
Well, like technically, we still have dinosaurs. They're like chickens, and we eat them for fun.
So how did T-Rex die?
I don't know. I'd have.
So how did the dinosaurs go extinct?
he's saying that they evolved to something that
No. 1 second.
How did dinosaurs evolve?
Wasn't it Ash?
I don't know.
That was Ash.
Yeah, like made it like the world like really cold.
Yeah.
And all that.
There we go. Because we found it. This crater. Impact crater buried beneath the peninsula in Mexico. I can't pronounce that word. Can someone help me? Excellent, thank you. What's this word? You sounded hesitant over that. You sounded hesitant. Yeah. It coincides with the Cretaceous, known as the KT boundary, and the now widely accepted that the resulting devastation and climate disruption caused a mass extinction of about 75% of plant and animal species on Earth, including all non-avian dinosaurs. One of the reasons we know a meteorite started the chain of events is that if we go through that particular layer, the KT boundary layer, we will find high amounts of, it's not iodine, there, maybe it mentions it. There's an element that is, there it is, a particular isotope of iridium, and we find that all around the world from when the asteroid got vaporized. Now, what was your question specifically on, though?
Well, how did I was just asking how you knew it was a meteor?
Oh, yeah. We found the meteor, but even before we found the meteor, we found the samples of iridium going, and that is really indicative that it was a meteorite, even before we found it. If it wasn't a meteor, something caused a worldwide event that caused everything to die. Another extinction event was probably caused just by a forest fire.
Which one?
I don't know. But at one point, we couldn't digest lignin, like no species on the planet could. And that's a major component of wood. And when then wood just accumulated. And at one point, there was a fire. We can find an ash layer that encircles our planet. And then eventually fungus evolved the ability to take it down, and now it actually gets properly digested. Yep.
Do dinosaurs like only live in hot places? Because I've never seen dinosaurs live in cold places. Like I've never seen a dinosaur in the snow.
Well, I've never seen them in hot places either. Because I've never seen a
I know,
dinosaur.
but like in the videos and stuff, I've never seen a dinosaur
Oh.
live in snow.
The problem is that we never see a dinosaur. What we see is people's conceptions of a dinosaur. So, for example, if we were to draw from the fossil record what a baboon would look like, we'd get that. Yeah. And if we were to draw a zebra, that's what we would draw from the bones. So all the dinosaur depictions you see are lacking a lot of flesh because we don't know what that would look like. So essentially, they just take the bones and they cover it in skin and say that's what the dinosaur looks like. They probably had feathers. They probably had loose, like, fleshy parts. That is an artist's depiction of a cat from its skeleton. Those are swans.
Oh my god. Is that a snake?
Python. Elephant.
That's not bad.
Yeah.
That's a wallet.
And there's what a human would look like. That's a human. Humans have a tailbone. So if you're going by the fossil record, you might think that there would be a tail and not just covered with flesh like it is right now. So it's part of your spine, but if you're an artist, you don't know that people have butt cheeks. So first of all, to answer your question, is that we're not properly putting them in their environment. So there may have been dinosaurs in cold areas of the earth. We do find their and remember, where we find their fossils is not what the climate is now. The climate millions of years ago, that land was actually in a different location. So that's why we find seashells at the top of mountains.
Really?
Oh yeah, because plate tectonics, the whole plate moves up.
Oh.
Yeah. So areas that were like far north are now south. So I don't know, I don't have in my head where the geographical distribution of fossils were and if they know that any of them were cold adapted. But it easily could be. You'd have to blame the artists. So all of Jurassic Park, if they actually made dinosaurs from, they probably have more feathers and stuff. Yep.
Are like mass extinctions, like, do they come, like, historically? Like, are we due for another one?
In 2183,
Like,
we are
you know,
due
like, history repeats itself?
for the next bubonic plague.
Was COVID a mass extinction?
No,
Because it didn't massively
we
extinct.
didn't massively extinct. It was just a global pandemic. About on time, every 100 years. But every 800 years, we get a global bubonic plague that kills off about 40% of our population. We're due in 2143.
Was COVID not one of them?
Oh, I think it was 20.
Sorry? No, it's a norovirus. Okay, moving on with definitions. Because you've distracted me long enough. What? Go away.
VPNs. I thought they're not allowed.
What? Oh no, watch this. Click. And now it thinks I'm in Alaska. Well, tease.
That's what they told us.
No. They told who?
Humans are not allowed to have VPNs.
No. Who's not allowed? Oh, are you the little student?
But then what's the point? What's the...
I don't want IT to see what I do.
So like if you want to log on to a Wi-Fi at Starbucks, it's probably not that safe. So like if you use it, it will like, I don't know what it does, but like it protects you. But like I think it just says you're in a place. I don't really know what it does, but it like protects you from the Wi-Fi.
Oh yeah, the follow-up question.
Okay. So, if we were to catch a feather or catch a piano,
Did you answer? Oh.
when we move an object over a distance, we have done work. And when we transform kinetic energy into something else, that is what the physics definition of work is. Yes? Okay. Bro? Kinetic energy is determined by the mass of the object and how fast it's going. So if I have a feather and I chuck it at you, you're probably not too worried because it doesn't have very much mass. If I put you on the ground floor, on one floor up in Privet House, I throw a feather on top of you, you're pretty good. If I take a piano, same gravity, just drop it on top of you, probably not so good. However, how could I make that feather more deadly? Just one feather.
Shoot it down.
Shoot it down.
You can.
Make it go faster. One of the more interesting museums I think I saw when I was in Vancouver, they have the police museum, and in there they have a display of all the items prisoners have made while being prisoners. and little tiny paper darts that are designed to actually puncture someone and do serious damage. Very light things, but they have a very blow tubes and other ways to make it move extremely quickly. So there's two parts to the energy of kinetic energy. Pearl? The two parts are the mass, piano versus feather, but there's also the velocity. How fast is it going? You're not really worried about a slow bullet. If I chucked a bullet at you, you're like, bang. But that bullet's moving extremely quickly out of a gun. Of course, much more worried. Yes.
The person that made like a paper saw on YouTube.
I have not.
It's like a person who like got like a circular piece of paper, like a small circle piece, attached it to like this thing which moved it really fast.
Really fast?
And then they sawed like different things with it, like wood.
Oh, that's very cool. Send me that, because that would be a good illustration of this. Okay. One more, and then we have some calculations that we're going to be doing. So mass and velocity, we've done mass. All objects have a position. When they change their position, they have a velocity. Do I have a... Does this spin very well? Yeah, it's not too bad. One of the ways you can tell that, can I spin very well? A little bit. Am I going to hit anything? No, maybe not. So if I'm spinning, this is actually really relaxing. What happens if I pull my legs in? I go faster, and then the chair almost goes over. If I spin when I'm close in, sorry, and then I put my legs out, what happened to my speed? Slow down. If I move my legs out, that mass has to travel a larger distance. That changes my overall energy. You can demonstrate it just in a chair. You don't have to go running around and do that. If you have that mass spinning out in that circle, it is moving a large distance. If I pull it in, it's moving a smaller distance. But the energy can't change. So where does that energy go into? So it was moving a big distance. I pulled it in, now it's moving a smaller distance. But the energy can't change, so that went into my speed. I sped up.
Yeah.
If it's already moving a small distance, so it's pulled in, and then I stick my feet out, it has to move a larger distance. I slowed down. Yeah.
What's the physics behind pumping your legs on a swing?
You are changing your center of gravity to apply the force in different positions. And so the work you are doing when you are like pumping is a bit like this to take advantage of that. So you go up. You're using your muscles, so you're converting that chemical energy by changing your center of mass. I can't, trying to think if there's a way that I can just express it verbally. I think I would need a diagram. Mr. Rodriguez would probably be better at that than me. But it's similar to this kind of a thing. Yeah. Okay. What have we got? I want to at least get up to the calculations. What just happened? Now the SI units of velocity is meters per second. And one of the things.
Direction and magnitude.
Where'd you get that from?
Oh yeah.
Meters, wait.
I'm glad he helped. So, in previous science classes, have you seen something like this before where I go delta first? What does that mean?
Square.
It doesn't mean squared.
Cube. Triangle.
Triangle. The delta means change in. So delta is equal to a change. Or final minus initial. So we would change, I would write that as a formula, and then I would go the distance that we ended up at, distance final, minus distance initial, over the final time minus the initial time.
What's the, what are you doing this completely?
The arrows refer to, say that again. What is a vector again? Vector.
It's direction magnitude.
So that refers to the direction. Because for any particular one, we're going to say this is north or west, and we're going to give a direction. If it changes direction, that changes the vector. Okay? So that just reminds, a speed is a velocity with no direction. If I just say I'm going 50 kilometers an hour, I haven't given you a vector, I've given you a speed. If I say I'm going 50 kilometers an hour due north, I've given you my vector. Okay? All of those with their handouts still open may close them and go. Those of you who have already packed up, please stay behind. Is yours still open? Nicely done. And for anybody that was watching this from the live stream, I'll put it back to our initial notes so they can grab those. So we started with the bottom of this.
Thank you, Mr. Thank you.
You have to be last.
Thank you.
You're welcome.
Thank you.
Oh, I forgot to do 3 minutes at the end.
Thank you.
Yeah. Oh, Elena, where are you going? Come back. Elena, at the end of class, you cannot stand up, put on your jacket, pack up. You have to wait until the class is over.
Can I end it now?
Now you can leave.
Thank you so much.
Thank you very much.